Okay, go. It's recording.
Alrighty, nuclear chemistry. Today we're going to explain this topic in the HSC outcome 5.1 and production of materials 9.2.
Turn it on.
Stable and radioactive isotopes. Isotopes are atoms of the same element with different atomic mass numbers, number of neutrons, but same atomic numbers, which is the number of protons. An isotope is classified as a radioactive once there is a spontaneous emission of radiation. These eventually become stable over time. There are two conditions in which an atom will be radioactive. Either the atomic number, which is all atoms with more than atomic number 83 are radioactive, so anything greater than 83 protons, or if the proton to neutron ratio is off, so the ratio of protons to neutrons determines whether an atom will be stable or not. There are three different types of radioactive decay, the first being alpha decay. Alpha radiation is composed of helium nuclei that are ejected from unstable large nuclei. For example, uranium-238. That's the equation for it. Beta positive radiation is made from positrons ejected from an unstable nucleus. It occurs when there is too many protons. And beta negative radiation is composed of electrons being ejected from the unstable nucleus. It occurs when there's too many neutrons.
Alrighty, so transuranic elements. Transuranic elements are the ones with an atomic number greater than 92, that is uranium. They are artificially synthesized, so basically they are made by humans and are not found in nature. There are two ways that they are produced. So the first one is neutron bombardment in a nuclear reactor, and the second way is the fusion reaction, which is made in a particle accelerator. So basically, neutron bombardment, the first step is basically they put an atom into a nuclear reactor, and then they get uranium to undergo a chain reaction. Now this chain reaction will produce neutrons, lots of neutrons, and the atom that we initially put, neutrons will be flung at it, thrown, and eventually after a lot of neutrons are thrown at it, eventually this atom will absorb one of those neutrons. And what will happen after that is the atom will have a lot more neutrons than it can actually handle. It will be unstable. So what will happen is the atom, such as uranium for example, when we throw a lot of neutrons at it and eventually it gains one, it will eject an electron, a negative electron. So a neutron, it will have 239 neutrons. So a neutron, it's made out of a plus and a negative. To eject one of these negative, to make a proton, as seen in here, where it throws an electron and then it has an extra proton, demonstrated by 92 to 93, and the overall neutron and proton, overall 239, is still the same. Next is the fusion reaction. Basically, fusion reaction is a little bit more complex, and it's used to produce a heavier transuranic element, or a larger transuranic element to be more specific. Now, these ones, they're a little bit more tricky. Basically, we need a particle accelerator to actually create them. A particle accelerator, basically, how we do it is we place a heavy nuclei in it, for example, uranium, and a positive particle, such as carbon. Now, the problem with that is, if we actually do get them together and just throw them at each other, they will not actually combine or fuse because of their repulsive forces. So the particle accelerator is actually used to move them at extremely high speeds to overcome the repulsive forces that are acting upon it. Now this is all physics, but we don't need to know it for the HSC. But all we need to know is that they are being flung at extremely high speeds due to the particle accelerator. Once that happens, basically it produces a CF transuranic element, which is extremely large. As you can see, 246 overall neutron and proton in itself, and 98 protons. And it will also produce a byproduct of 4 neutrons. Now, production of commercial isotopes. Commercial isotopes are ones that are radioactive and are produced on a regular basis for medical and industries. Now, usually for elements such as cobalt and technetium-99, which are both used for medical and industrial purposes, we make them at the Lucas Heights nuclear reactor in Sydney, because that's the only place in Australia that we actually have one, from my assumption. And for fusion reactions where we make heavier, larger transuranic elements, it's found at the National Medical Cyclotron near the Royal Prince Alfred Hospital. an example of things that we produce is iodine 131 and carbon 11. Now we'll expand on these medical uses and industrial uses in later outcomes, such as 9.5, which Islam will discuss later on. Instruments used to detect radiation. Now, this outcome is a little bit tricky because in the outcome, it actually states to identify F2, because of the plural, S, in the outcome. However, it's not necessarily that we actually memorize 2, because they may block us out. For example, they may say, a question might pop up like this. X and Y are used to detect radiation. What's another example of something that detects radiation? So it's optimal to actually memorize 3 so that the HSC cannot, defeat you, to say the least. 3 examples are the Gigeler-Moore counter, the photographic film, and the scintillation counter. Now, the best one to actually know in detail is the photographic film, and that is because it can be used for all types of radiation. So in any multiple choice, if you see a question about radiation, detect radiation, if you see photographic film, it's almost certain that is the correct answer, because in regards to radiation, it gets all types of radiation, alpha, beta, and gamma. Now, in regards to photographic film, how does it work? Well, basically, in regards to how it works, basically a photographic film is a sheet of plastic coated with silver halide salts. Now, as the electromagnetic radiations get stronger, the sheet will actually begin to darken. The stronger it is, the more it will darken. Usually, this is actually used in radiation sites by workers. If you haven't seen workers, they actually wear a logo with that black sheet to actually, the silver halide sheet, sorry, and to identify if there's actually a higher level of radiation around them to protect them.
The use of a named radioisotope. In industry, Pebble 60 is used to project radiation into large metal sheets in order to detect any faults in the infrastructure. This is done through the detection of larger amounts of radiation by photographic film. In medicine, Pebble 60 is used as a cancer treatment method, projecting high energy gamma radiation at mutated cells in order to kill them. There are advantages and disadvantages to using radiation to do different stuff. Advantages is that gamma rays have sufficient energy to destroy specific cells, but not enough to irradiate the organism completely. It also has a half-life of 5.3 years, so it can be used for an elongated time, and it offers a wide range of non-invasive diagnostic and treatment techniques. However, there is plenty of disadvantages to these advantages, some consisting of the gamma radiation may be extremely dangerous in large amounts, protection from continuous exposure must be maintained, and used radioisotopes are still slightly radioactive and must be stored for millions of years without contact.
Alrighty, so question. Now this is worth 3 marks. Now to read the question, iodine 131 decays through both beta and gamma emission. Iodine 123 decays through gamma emission only. Iodine 131 is used for diagnosis and therapy, whereas iodine 123 is used for only diagnosis. They give us some information, which is beta emission emits electrons and has low penetrating ability, and gamma emission emits gamma radiation and has high penetrating ability. Now, with reference to the information, justify the different uses of these radioisotopes. So we can see that both of these, iodine 123 and iodine 131, can be used for diagnosis. Now, this is because they both emit gamma emission as portrayed in the information. However, why is gamma emission actually good for diagnosis? Now, the reason being is it has a high penetrating ability, which is good for diagnosis because the machine, as you inject it into your body, that goes through and identifies the tumor, the machine needs to actually detect the radiation. So if it has a low penetrating ability, the machine will not be able to detect it. Hence, both of them, the ones that emit gamma radiation, can be used for diagnosis. However, what makes iodine 131 so special, in which it's used to both kill tumors and diagnosis, is because it also emits beta emission. Now, what this does is, due to its high low penetrating ability, now we all know that radiation is actually able to affect cells. Now, since it's able to affect cells, it would be wise to use something that's low penetrating ability for a more precisely aim the tumor that you're actually looking for to kill it. If it had a high penetrating ability, it would actually penetrate through a lot of other cells and actually kill the healthy cells as well, which is not wise when undergoing treatment. Now, question 23, HSC question, now 3 marks. Element 112 was first synthesized in 1996 and officially named in 2009 as propinicum, CN278. Explain why the transuranic isotope CN is unstable. Now, the good thing about this is Islam identified this in his own slide where he talked about how things above 83 are usually unstable. And why that is because the proton to neutron ratio is different. Elements before 20 from my mind usually have a 1-to-1 ratio. However, as you increase from 20 to around 50, you'll see that the ratio increases to 1 to 1.3. As you reach 83 and a little bit less, you will be looking at 1 to 1.5. Now, if the element has even higher atomic radius, then it will be counted as unstable because the ratios are way too different. Now, in regards to element 112 CN278, it can be written as this, which means there is 112 protons, and overall the neutron and proton count is 278. So to find the amount of neutrons there is, you do 278 minus 112, which by memory is 116. Now 116, if you look at the ratio 112 to 116, this ratio actually acts as an element that has a 1-to-1 ratio, which is not true by the definition because atomic number.
You spelled it wrong.
66.
It's not 116.
Alrighty.
By memory. Your memory is wrong.
My mind's a rendering.
Don't cut it out.
Oh, don't cut. Keep going. Keep going. Keep going. Keep going. No, bro. Don't cut it. Don't cut it.
Alrighty.
The other one as well. Wait, from memory, the other one as well.
Oh, from memory? Yeah.
Yeah, that one.
Boys, this is unprofessional.
For my mind.
Alright.
Alright, so after radar identification by Halil Aydwan, it was actually 166. However, there's still, if you use mathematics to actually calculate it, the ratio still doesn't apply to something that is greater than this. And hence you can identify the fact that it is a transuranic isotope is unstable because the ratio is not much greater, which is not true. In regards to B, describe a method by which transuranic elements can be synthesized. Now, I already went through this, so I don't think I need to answer it, but you can pick either particle accelerators, so nuclear fusion, or nuclear reactors, which is basically neutron bombardment, and describe it, so you give detailed explanation to it. And obviously an equation depending on the amount of marks, but it's always much safer to actually include an equation. Thank you for listening to my video.